class, hopefully I will have like 1 hour to go over the different applications of power electronics. It's just I'll talk about everything, SVC, what's SVC? Electric car, I don't know. Like talk about the solar farms, how they work, all these different applications, this kind of application. I want to talk, just give you a kind of picture of this kind of things, You can see how wide is power electronics, how wide they can use the power electronics with everything. Simple power supply to go to a huge, I don't know, if they call it pulse power also. In GA, we have a nuclear facility, they create plasma. To create plasma, they need a very, 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 very high voltage, to generate that kind of, and very high power. So they use it, they call it pulse power converters. They use those ones. It's going to be a short time, like 10 seconds, but it's about how many megawatts? I think we are pulling about like 15 megawatt of power during that time, that short time, And to create that plasma inside, they call it D3D because it's like a donut. It's like a D, letter D, and it's like a three-dimensional. That's the area they generate that plasma in the nuclear facility. I haven't worked with that because it's not my major at all, but to create that one, they need a huge, huge power supply, which is what I do, and we work on that kind of. So let's finish these two more, circuits we need to discuss. And after that, I'm going to talk about phase 4. Phase 4, there is one PI controller you need to implement. It should be very simple. I tried to find the example here in Copy. I find it on my computer. And after that, I'll talk a little bit about the MPPT, how you should implement it in your simulation. If you are effective, you should be able to finish it in 1 night or 2 nights. That's it. It shouldn't be that much. And you spend maybe 1 night or 2 nights to write a report. Or send an email. We don't need more than 15 pages of presentation for the day you are coming. So as I said, you do a kind of work together. Not one person is going to present. It's going to be kind of all together. You present it. You can come sit down, ask questions if you want from your friends. That's welcome. This is like a presentation. You go present the paper in IEEE somewhere. People will ask you questions. If they're your friend, they don't ask questions. I'll ask questions. And if they do or not, I'm going to ask some questions myself. And right away. And we will go for the exam. Exam 4 questions. 4 questions. 1 on resonant converter, 1 on the inverters, and 1 on the, I don't know, this small signal things. We talked about it, and the state space equation. We will have two questions there. I'll tell Arnold to upload the last year final. So you guys, one of them is your homework number 2. 1 or 2. It's very similar to the homeworks we have. Very simple examples, and a simple exam, And I'll tell Arnold to upload it for you guys. This year I taught the resonant converter more than last year. That's the only part of that. Now we go with we talked about this DC today. Series resonant DC to DC converter. Now we're going to talk about the parallel. Parallel resonant. Again, we are going to go with the half bridge. We had this circuit. call this one VCR. VR1, VR3, VR2, VR4. Let's call this one IX, and that one is IX. Let's see. I'm going to put the assumptions here. So if the CO is very big, what is going to happen? What is going to happen? VO right? If the capacitor is very big, the voltage is almost constant. If L0 is very big or LO is very big, how about that? Right? So this one is going to filter the current, this one is going to filter the voltage, right? So let's have these two assumptions. Now we're going to think about this circuit, how it's going to work. And whatever I'm going to say here, this is for, we are going to talk about omega more than omega 0. What was the omega 0? Resonant frequency. This is what I'm talking about here. Is going to be for omega more than omega 0, which means circuit is inductive, right? When omega is more than omega 0, XL is going to be more than XC, right? Because XC is 1 over C omega, right? Add omega equal to omega 0, they are equal, right? They are going to cancel each other. But if omega is a little bit more than omega 0, means XL is going to be bigger, XC is going to be smaller. Why? Because XC is 1 over C omega, right? If omega is getting bigger, XC is going to be smaller, right? We can see here, XC in general is 1 over C omega, and XL is L omega, right? At omega equal to omega 0, XC is equal to XL, right? They cancel each other. If omega is a little bit more than omega 0, XL is going to be more than XC, right? So just we're going to discuss this case. The case omega is more than omega 0. So I'm not going to go to the detail. There are lots of detail about it. If omega is less than omega 0 and more than half of omega 0, and the other part, I'm not going to do those ones. They're going to get to the discontinuous mode. We'll discuss only this case. Now, let's call this one A and B again, and C and D again. Let's see how this circuit works first, before writing anything. Let's look at it here. We have two parameters here to look at, ILR and VCR, right? Last time it was only ILR because this two they were in series, right? And we could discuss it. If ILR is positive, so basically this one and this one should be on, right? And if ILR was negative, this one and this one should be on, right? Now we have it a little bit different. Because this ILR is not going to go to there, right? ILR, I don't know, part of it is going to come here, part of it is going to go over there, right? Now, but again we'll discuss the ILR. If ILR is positive, which one is on? S1, right? Yes. And V2. And if ILR is, and if S1 is on, how much is VAB? V in over 2, right? If this one is closed, this point is connected to V in, this point is connected to V in over 2, and another assumption here, C1 is equal to C2, and they are very, very big, right? Which means what is going to happen? VC1 is equal to VC2 is equal to V in over 2, right? So these are the assumptions we have. I should have write this one also here, no? So these two capacitors, they are equal and very big, right? So basically it's going to result in, this one is a V in over 2, this one is a V in over 2, right? Now, if S1 is on, this point is connected here to V in, this one is connected here to V in over 2. How much is the difference? Positive V in over 2, right? If we said if the IR is positive, it's going to be either this one or this one, right? If this one is on, this is connected to 0, this one is connected to V in, so VAB is going to be minus V in, right? We discussed this one before. Now if ILR is negative, the other way. So D1 or S2 there could be on. If D1 is on, the VAB is V in over 2. If this one is on, again is a minus VA over 2, right? So from this side. Now, let's look at this side now. This is new. First of all, this current is a DC current. Remember, in the power electronics one, we call it highly inductive load, right? When as soon as we mentioned it is a highly inductive load, means the current is constant, right? Now we are saying the same thing. L is very big, so basically the current is constant, right? Now, this current either can go through here, right? Through here, D1 and D2, right? This current is not going to change its direction. It's always this way, right? Or can go through what? Can go through here. Right? There's going to be two paths. D1, L0, VO, D2, or D3, L0, VO, D4, right? Now, not D, DR1, DR2, there is a R. Let's look at this voltage. If this voltage is going to be very close to sinusoidal waveform, this is like a similar discussion like what we had for the inductor current. We said it's going to be very, very, very close to the sinusoidal waveform. Why? If you remember, we said if there is a high Q, the harmonics in the current is going to be small, so the current is going to be very, very close to the sine waveform, right? Here also we assume the voltage of capacitor is sinusoidal, but it's going to be shifted from what we have here. Now, if this voltage is positive, which one is on? DR1 and DR2. This is like a diode rectifier, right? If this voltage is positive, this one is on, right? And if this voltage is negative, these two they are on, right? So that is as simple as what I said. This is circuit analysis, and we'll come up with the R effective. We need to find the again relation between the input voltage and the output voltage. That's what we want to know, the gain. If you're going to control it, how much gain. For example, he said, if I want to have, for example, I don't know, 10 volt at the output, and how much and my LR and CR is this much. These are like problems you solve. How much should be my input voltage? So you can find out the R effective, and you find out the resonant frequency, Q, those kind of things. We'll go through those equations, and finally you find out how much is the VE. You can do that. And another thing you are getting familiar. Look at here. This is what we had in power electronics 1, right? That was a half bridge, right? We talked about this one toward the very end. This is the diode rectifier. We talked about it at the very end of power electronics 1, right? My point is, you go a little bit further, the circuits are all, like blocks. You know what I'm saying? You just combine them together, or you come up with a new circuit topology. My point is, see, we learn these things, now we start to use them. You know what I'm saying? As a block. We're not going to discuss this one, how this circuit works, because already we know. This is the full wave rectifier. Or it could be another bridge here. It could be another bridge here. I'm not going to talk about the bridge, but because right now, if you look at it, only power can go this way, right? Power can go this way or not? Why not? Because this diode, they don't let you the power loop. This diode, they let you only the current go this way, right? And if you want to make it bidirectional, you have to have another bridge here. So let's go that way, right? We're not going to talk about the bidirectional one, but this is the unidirectional. But my point is, if you want to, for example, on some of the electric cars, they are thinking to use a resonant converter for charging the batteries, you know. And so if it's only charging, still you need the unidirectional, right? You plug it to the, I don't know, charger or wherever you want, and you charge your battery. But some people, they are thinking to use the electric cars like a mobile UPS. If you have a big battery pack over there, right? If you have a big battery pack over there, why not use it as a UPS? You know, if I need the AC voltage somehow, right? So I have a, I don't know, old time, they used to move the TV with them, they go to picnic somewhere, right? To watch, for example, I don't know, football game or whatever they want to see. Why I don't use my car as a UPS? You know, I have an AC voltage, I can plug in my TV and watch it. Or I don't know, another thing, laptops, you know, you can see for laptops, there's this converter, they plug it to the, there is an outlet in the car, it's a 12 volt. I'm not sure how many of you guys have seen that one. You can plug it that way, you can connect it to your laptop, you know. This is another converter. Nowadays, they're thinking, hey, let's make the car bidirectional. They're another energy source. We have a battery. If we don't use it, let's use it, you know, for the peak shaving, right? For example, you're sitting at home. Your car is fully charged, right? It's, I don't know, 6 to 8 p.m. and you're not going to go home anymore, out anymore. Why not use the energy in the battery to support your load? You know, for example, you have some light, something like that, right? And say, okay, hey, when is it 10 p.m. or I don't know, 11 p.m., I'll charge my battery back. Tomorrow morning I'm going to leave, I want my battery will be full charge. You know what I'm saying? You can use this battery as a small storage to do the peak shaving, right? To reduce your electricity bill. You can do that way, you know, you can use it. My point is, when you get to that point, you are going to use, for example, your car as a UPS. So battery is here, instead of resistor, I'm putting here is the battery, right? For the, so now it's okay, I'm going to take the power back. So this one has to be bidirectional. Charge, discharge, right? Usually battery in the car, the battery, is connected to the drivetrain. To the drivetrain here, there is an inverter here, like the inverter is stimulated. And there is an AC motor, that's a permanent magnet motor. So it drives that motor, you know, to move your car. But when you are going to go to the UPS mode, you know, the car is not running anymore, so the battery will be disconnected from the inverter and those kind of things. Basically, you can use it this way. Now later on, you're going to use this battery, so charge it here, right? Charge your car here, your battery here, and tomorrow morning you're going to go, you can use it again like an electric car. My point is, nowadays they are doing a lot because there is lots of flexibility, you know. If you talk about this thing maybe 20 years ago, to put something like this, it's going to be huge and you cannot put it in the car because it's going to be heavy to move it around, right? But nowadays everything is getting smaller, 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 more efficient, less loss, and all those kind of things is thinking, you know, giving this flexibility to people, you know, hey, let's use more. I have this battery, why just I should use it for my car to drive it? I use it to reduce my electricity bill, right? So that's the advantage of, you know, advancement of power electronics and devices and all those kind of things. Now, so we talked about this circuit, how it's going to work. I'm going to put the circuit here. Basically, very simple, you know. Look at here, this is like a current, right? Common current. If you look at this system, from here to here, what you're going to see, you're going to see something like this. It's going to be plus minus V in over 2, right? Based on which mode we are. Based on switch 1 is on or V2 is on, you know, it's going to be either plus V in over 2 or minus V in over 2. Now, we're going to have a LR, ILR, VCR, CR. If you look at here, it's going to be like this. minus I0. Let's say why I say plus minus I0. We say this current is all the time like this I0, right? If these two they are on, right? Here we are gonna have I0 like this, right? If these two they are on, right? What is gonna happen? The I0 is gonna come from here, going this way, right? So basically, if you look at here, it's like a current source. It could be this way or that way, right? So that's the reason I put the plus minus I0 here. And this is C and D. Now, let me write the modes here and the modes we have here. If ILR is positive, so either S1 is on or D2 on, right? So either S1 is on or D2 is on, right? Now there is another condition. So we decided, now we need to look at the VCR, right? If VCR is positive, which one is on? If VCR is positive, DR1 and DR2, right? DR1 and DR2. So if DR1 and DR2 they are on, how much is IX? Oh, I forgot to put this one. Let me put it. Oh, I did here. How much is the VAB first here? No, I'm writing it really bad. Let me see. Oh, I'll put it here. Let me see. I'm writing really bad. Let me see. Let me correct it one. So we are going to have two cases, right? Either S1 is on, right, or D2 is on, right? In this case, VAB, how much is it if this one is on? This one is going to be plus V in over 2, and this one is going to be minus V in over 2, right? Now, if VCR is positive, which one is on? DR1 is on and DR2 is on, right? And how much is the IX? How much is the IX? IO, positive IO, right? Or IX. Again, if VCR is positive, right? So DR1 is on for both cases, and DR2 is on, and IX is again positive ion, right? Now, another case, this one is positive, this one is negative, right? Yeah. If this one is, oh, we didn't discuss that one. If VCR can be positive, how I can summarize this one in case. Now we say if ILR again positive, right? Again the same thing, S1 is on, D2 is on, and VAB is V in over 2 and minus V in over 2, right? And now if VCR is negative, right? Which one is on? If VCR is negative, these two are on, right? DR3 on and DR4 on. Again, the same thing here. So how much is the IX? Minus I0, right? We can repeat the same thing for ILR negative, right? So I want to try to see how I can put everything in one. ILR negative. I have to write it like this. The another case is like this. If ILR negative, right? Which one they are on? ILR negative. Negative means this current is going this way, right? Either it can go through D1 or it can go through S2. So if D1 is on, it's going to be V in over 2, right? If S2 is on, it's going to be V in over minus V in over 2. Now here, again, two cases. If VCR is positive, again, the same thing like here. DR1 and DR2 are on. DR1 and DR2 they are on. And IX is I0. Right? I'm going to put the graph and put all these cases together. And the last case we have, if ILR negative, VCR negative, right? Both of them negative. So, if ILR negative, again the same thing, right? D1 on, S2 on, again here, V in over 2 minus V in over 2. If VCR is negative means positive, negative, positive, DR3 and DR4 they are on. DR3 and DR4 they are on, and the current is minus X, right? Now I'll summarize all these four tables in one graph. Now I'll put everything in one graph and we'll go over it to see how is that. Let's start with the VAB. So this one is going to be V in over 2 and minus V in over 2, right? Now, if you look at the ILR and the VCR, let's put the VCR first here. VCR is going to be like this. Gain. I'm trying to do it now. It's going to repeat, you know, and yes. So we say the VCR is going to be, and this is the fundamental. Let's put one here. Let's put one here. VCR1, the fundamental of the VCR. Now, if you look at the ILR, how is it going to look like? This current, you know this voltage and you know this voltage, you can plug the ILR, right? Look at here. dILR over dt during this time is this voltage, right? Minus this voltage. Maybe like this. All the way, it's not going to happen at the zero of this one at the same time. So it's going to be something like this. And again, let me see when we finish it. Something like this. And again here, it goes something like this. And something like this. This is what we have for the current. Basically is during this time, it's going to be positive slope, so the current is increasing. During this time, it's going to be negative slope, the current is decreasing. And again is happening, you know. The detail of what is the equation and those kind of things, you can write the equation, your differential equation and find it, but we don't care about that right now. Now, let's look at, see, which one is on and when. Which one is on? Here. This modes we have here. Here, ILR is from here to here. From here to here. So, ILR is negative, right? VCR is negative. So which ones they are on? ILR is negative. So which one is on? And VAB is positive.
DR3 and DR4 and D1, DR3 and DR4.
Now what about with this? Let's see if this one doesn't happen or not. If VAB is on, yes, so that's the current. If VAB, see look at the VAB is positive, right? During this time, right? So which one is on? D1 or S1, one of those two. But the current is negative, right? So basically D1 is on, right? So here we have a D1 on, and who else? D1 coming. Now, let's look at here. VCR is negative. So VCR is negative. So means which one they are on? DR3 and DR4. Right? If we go from here to here, it's very narrow, I cannot write it, you know. What is happening here? See, still the VCR is negative, right? Still DR3 and DR3 and 4, they are on, right? But, and VAB is positive, so either D1 or S1, but the current is positive. Which one is on? S1 is on. So it's a little bit difficult to write it here. It's going to be S1, DR3, DR4. right? With this for the narrow part. If you come here, from here to here, still V in is positive, either D1 or S1, right? The current is positive. Which one? S1, and VCR is positive. DR1 and 2. Right? And you can keep going and find for all these modes which one is on, which one is off, right? Now, let me do a few more here. Let me do a few more here. Can you guys read? There is a 1 here, 1 here, 1 here, another 1 here. These are the next one is going to be yes here, and after this one we're going to have another one here. Right? These are the cases we have. Here, voltage is negative, current is positive. Which one? D2. D2. Going to be D2. VCR is positive, DR1 and DR2, right? Again, I don't know. We'll do the rest. Now I'm not going to go through the rest. Let's see. Now, if you look at the switch current, just let me see. We had a D1, S1. Look at here, guys. S1, S1, again D2, right? If I want to plot the switch current, IS1. So IS1 started from here when the current is positive, right? Till here, right? It's going to be like this. So it's going to go up to here. Right? Here the current was positive, but the voltage is negative, so we switch to the D2, right? The current is going to be for S1 is going to be like this. Right? Clear or not? Now, I'm not going to plot the rest, that's going to take time. But, let's plot the VS1. Why we are doing all this kind of thing? We're going to talk about the soft switching. Soft switching, what does it mean? Means we are switching at either voltage 0 or current 0. We are going to see, we are going to show you this circuit is going to do that, at least at one side. One side is going to do that. Now, let's do the VS1. So during this time, how much was VS1? Because it's on, right? Look at here. Who is on? D1. So basically, it's still here is 0, right? If the D1 is on, these graphs are not in your book. Just to let you know, this is not in your book. And this one, because the D1 is on, still the voltage is here. If D1 is on, right? How much is the voltage here? 0, right? So, but after this point, right? Who is on? D2. D2 is on. D2 is on. If this one is on, how much is the voltage here? This one is short, right? So how much is the voltage here? One side connected here, one side is a V in, right? It's going to be V in. Until, I don't know, we need to go through this sequence to see again when D1 is going to start. Yeah, basically, we know when the D1 is going to start. D1 is going to be on here, right? Or here. Right? The current is negative. Yes, the current is negative here. If you look at here, D1 is on. Voltage is positive. The current is negative. So basically up to here, this voltage is going to be in, and after that again it's going to be 0 up to this point again, right? So basically if you do it here, it's going to repeat here. And how much is this one? 3. What does it mean here? Either zero voltage or zero current switching, right? Right or not? You can check the same thing for this side also. You know what I'm saying? To see is there any soft switching on this side or not? Because these are diodes also, alright? They're gonna turn on, turn off. It would be good if they turn on and turn off at either zero current or zero voltage, right? So, but we are focusing on this one because this is under our control. We are going to turn on, turn off, turn on, turn off, right? This is what we are doing. We can control here. So let's plot the Ix also. So how's Ix? We had a DR3 and DR4 on, DR3 and DR4 on up to here, right? If 3 and 4 they are on, how much is Ix? If DR3 and 4 they are on, how much is Ix? Minus I0, right? Minus I0. So basically here is going to be minus I0, right? So when R1 and R2 they are on, up to here, basically up to here, right? It's going to be how much? It's going to be what? I0, because D1 and DR1 and DR2 they are on, right? So this is I0. And again here, what about here? The voltage is negative, right? So 3 and 4 they are going to be on. And keep going. Right? Now, let's see how we can model this circuit. How about V81? How much is a V81? Guys, tell me. 4 over pi times, right? That's a fundamental of that one. So it's going to be 2 V in over 2, right? Over pi, sorry. Over pi. Right. Now, how about the VCD and ICD? Sorry, I'm saying the current going through the ICD. Let's call it ICD1. How about that? How much is the ICD1? How much is it? This is the ICD, right? This is the ICD, right? And this is the IX. Basically, the IX is the ICD, right? This is the IX, right? Right. How much is the fundamental of ICD1? Isn't it 4 over pi I0? That's a Fourier transform, right? So now we know ICD1. To find the equivalent resistor here for the fundamental harmonics, right? I need to find the I can say VCR1, right? Divided by the fundamental of this one, right? If I know how much is the fundamental voltage, how much is the fundamental current, I can divide them by each other. I find out how much is my R effective here, right? So as I put it here and I mentioned, there was another assumption. We assume the VCR is a, for example, VCR1 sine of omega t plus something, right? We assume this voltage is a sinusoidal, right? We did assume that. With the value, the maximum value of VCR1, right? Let's see what's the relation. If this one is a sinusoidal voltage, let's see what's the relation between here and here. Relation between here and here, right? So how much is the V0 and VCR? What's the relation between V0 and VCR? From power electronics 1, if you have a source like this, the maximum is Vm, right? And you have a diode, and you have a load here. If this one, the maximum is Vm, how much was this thing? DC voltage. 2 Vm over pi, right? That was simple equation. 2 Vm over pi. If it was a half wave, it was a Vm over pi, right? For the full wave, it was a 2 Vm over pi. So basically, V0, right, is equal to V2 Vm, which is the 2 VCR1. Look at that equation over there. Over pi, right? Or VCR1 is equal to pi over 2 V0, right?
Wait, why isn't it equal to 2 VCR? Why is it equal to VCR1?
Huh?
Why is it equal to VCR1? And not like VCR1 times sine of whatever?
Max.
I'm not
Oh, just
following.
the max? Okay, never
This
mind.
is a max here,
Okay, yeah.
right? I call it the maximum value of the fundamental harmonics here, right? Now, so if I want to find out how much is my R effective here, what should I do? VCR1 divided by, I said VCR, ICD1, sorry, VCD1 divided by ICD1, right? So R effective is going to be VCD1 divided by ICD1. How much is the VCD1? Is a VCR1, right? This is CD, right? This is CD, basically the VCR1, right? So the fundamental of VCD1 is the VCR1 divided by ICD1. How much was it? I have this one, right? And let's say replace this one also with this. Right? How much is the V0 over I0? We say this is the I0, right? How much is the current here also? It is I0, right? It is a ripple free, right? There is basically nothing going here. But in reality, we need to have this capacitor. So V0 over I0, how much is it?
R.
Is R. So R effective, like the previous one we had, is going to be P to the power of 2A R. Now, I can rewrite the equation and wrap it up. I'm going to put it here. Here. This one is going to be VAB1, right? We solve the circuit for the fundamental, right? And here is going to be what? RE. Or this one is a VCD1, right? Right? RE and the voltage across that is a VCD1, right? Now, what is the goal here? What is the goal? What do you want to find out? Hmm? What do I want to find out? I want to find out the relation between this and this, right? V in and V out. Let's write it down. So, how much is the VCD1? The voltage divider, right? You can say one impedance here, right? These two parallel, right? Basically, it's going to be this divided by these two together, right? So if you write it, it's going to be like this. VCD1 over this is going to be, I'm going to go with the admittance of this one and reverse it because admittance is easier to write down. How much is the admittance of this one? J omega CR, right? How much is the admittance of this one? Right? So 1 over this is the impedance of this one, right? Agree or not? Is it strange or is it okay? Okay, so that's it. So basically this is like you have a Z1 and Z2, right? You say Z2 over Z1 plus Z2, right? And now Z2 itself, it could be 1 over Y2, right? Let's assume Z2 is like this, something like this, R and C, right? How much is the Y2? Y2 is R plus JC omega, right? Yeah, you can say these are parallel, right? You can say from admittance side, you say this one plus this, 1 over R, sorry, 1 over R, right? And after that, you say Z2 is 1 over this one, right? Now, here is going to be, this impedance is the J omega LR plus this impedance, right? 1 over RE plus J omega CR. VAB1. Right? Now just you care about only the amplitude of this one, right? If you simplify that one, you can get it to this way. You can say it's going to be if you simplify it, it's going to be something like this. Yes. Now, but what I'm looking is not VCD1 and VAB1. What I'm looking for, V in and V out, right? Let's put it here. How much is the VCD1? Yeah, you wonder, right? How much is the VCD1? Again, somewhere here. I over 2 over the VCR, but VCD and VCR, they are the same. VCR and VCD, they are the same, right? So it's going to be this much, right? Pi over 2 VO. How much is the VAB1? 2 pi V in, right? Just replace them here, right? You're going to get the relation between the V in and V out. So basically, Now, if you plot the if you plot the graph for this one, then like this. V over VE, and this is the omega over omega 0. For example, this is the Q5. For example, this is the Q4. This is the Q3. This peak, I don't know how much it is. There is some number. You know, we don't know how much it is. Now, this is a 1. This is the resonant frequency, right? And if you look at it here, this one can go to 0. This one is going to go down. Now, if you are going to control the voltage, say, for example, let's say again the V in is 24 volt. For this case, for some, it depends on the values of LR and CR and those things. But for example, here, for one case, this one was, for example, 2.5, for example. Now, you could have some boost also, right? If V in is 10 volt, right? If I set this one, for example, here, I want to have a 20 volt. If I plot the 2 volt, sorry, line 2, right? I'm going to work here, 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 or here. You said we are going to work for omegas more than resonant frequency, right? We are going to be here. So basically, if my Q, this is what you need to define. What kind of load you have, how much your load is going to vary, right? For example, if your load is going to come to this line, we cannot provide, 2 times of the V in, right? So for example, somewhere here would be the answer, right? This is the minimum Q I'm going to have. This is the maximum Q. This line should cut all of them. Which means, okay, if I have this much load, I switch at this frequency. If I have that much load, I switch at this frequency. If I have that much load, I switch at this frequency. So basically, I'm going to get, for example, 1, ratio of 1, right? So my VO is all the time is going to be equal to VE, right? Or I don't know, 0.5 of that one, right? So basically, you should make sure, this is a design. I'll show you in the Infineon problem we're doing. You should make sure this line is going to cut all these things. So, and your switch can change this much, switching frequency. So the next one I want to talk about it is the series parallel. Series parallel. I'm not going to go through the detail and all the waveform. It's going to be, let's call this one CS, and this one CP. I forgot this. Just my point is, the tank, they call this resonant tank. You know what I'm saying? We are going to have LCP, right? So the discussion is very, very similar to what we have for the parallel converter. The only thing at the end is this one. For the series parallel, see, 1, 2, 3 capacitors, right? These curves, they are going to change. You are going to have more tool to change these curves. You know what I'm saying? The more parameters you have here, you can move this curve a little. So for example, see here, I put in cross this one here, right? It's going to give you a little bit more, flexibility to move this curve, based on what you need. If you do this one, the series parallel, they call it hybrid, series parallel. So basically, VO over V in is going to be V over V in is going to be like what we have here, 4 over pi squared times 1 over 1 minus, make sure this is the 1, no, it's not, no. It's going to be 4 over pi squared, so this is a xc over xcs over xp, sorry, cp plus minus xl over xcp absolute value of this plus j xl over re minus xcs over r. That's the case. Again, this is a very, it looks a little bit maybe big, but that's exactly what we discussed here. I'm not going to go through that one anymore. So for the series parallel, V over V, you can see 4 over pi squared. 4 over pi squared we had here for the parallel case, right? So it's going to be this one, this is the real part, and this one is going to be imaginary part. So if resonant is going to happen, these two, there's one here, right? And there's another one here. Got it? Can you think about it? See? Either this one can be 0, right? What does it mean resonant? You're going to get the max, right? We say here is the resonant frequency, right? When with the curve we have something like this, what does it mean? We have 2, right? So look at here. I can select this one to minimize this. Somehow this one will be equal to this one, right? This is 0, right? Or this one will be 0, right? 2 resonant frequencies. Then you have a series circuit. Let's say there's one here, right? Just think about it. L is a little bit more than this one, right? Effectively, it looks like we have an L here, right? The L is L minus C, right? Now I have one L here and one C here. It's going to be like this, right? There's one resonant frequency here, right? And there's one resonant frequency here, right? So there are 2 resonant frequencies. It's going to give you a little bit more, options for this kind of. Another one, this is just a circuit. Now I'm going to show you. I'm not going to discuss the results. So if you want to, for example, isolated one, I'll go back to the very first. Isolated series resonant converter. I'm not going to discuss the circuit at all, in the detail of the circuit, but let's see what it is. So series, the one we discussed was like this, right? V in C1, C2, right? This is what we have, right? Up to here. The same thing. Isolation. What do I need now? I should have a full wave rectifier on the other side, right? Here I have an option. I'm going to plug the first option, the easy, the one comes to mind. How about this? This is the LR CR, right? Some people they said, why should we put 4 diodes? I'll do this way. You can do this with us. Can you remember the center tap, full wave rectifier? Right? That's a full wave rectifier with the center tap transformer, right? Some people they said, okay, if you're gonna have we don't have a full bridge, it's a half bridge, right? Why do I put this capacitor here? This one is going to be my resonance circuit when this one is on, and this one is going to be my resonance circuit so basically I don't put the CR here anymore, right? They move it here. So I'm saying these are circuit topologies. He said we are going to save on the capacitors. You know what I'm saying? We are going to save on the capacitor what we have. If it's a full bridge, you cannot, right? If it was a full bridge, see, if it was a full bridge, this is a full bridge, right? All we discussed it was a half bridge. You put it a half bridge, but it could be full bridge, right? If it's a full bridge, you have to have both, right? Because there is no capacitor here to use it for resonance, right? You have to have the capacitor here. But if it's a half bridge, to create the half wave voltage here, right? You have to use this capacitor. I think I'm going to use this one for my resonant also, right? This is my resonant loop, and they are in series, right? When this one is off, think about it. It's coming from here, LR, coming here, CR, right? This is my loop. So I don't have to have extra capacitor, right? So this is a different one, Tuesday I'll talk about the Infineon, circuit. Infineon circuit is like this. It could be half bridge, full bridge, whatever here, but it's like this. They call it LLC. They call it LLC. It's like this. I don't care about the rest, over there. You remember from the transformers, they have a LM, right? At one end, and I have one L here, and C. They call it LLC. That's a very popular resonant converter. We'll discuss this one, how to design this one. We'll go through the note. The note is very complete. You discuss everything in the note. It's like 20, 30 pages. If one day you want to design something like that, that note is pretty good. I use it myself for a design I did in the company. Now, I want to talk a little bit about the phase 4. I want to talk a little bit about phase 4. And any question here? It was easy, right? Simple. Okay. Let's talk about the phase 4 now. Can I erase it? It's okay. I thought it's good to mention the resonant converter. Maybe it was a little bit too much to push it toward the end of quarter. Now you know what's the resonant converter. I'm not saying you're expert, but somehow you know what's the resonant converter. There is an L and C. They're resonating and they're generating this kind of current and voltages. So if somebody tells you, do you know what's resonant converter? You say, I know a little bit about it. And if you're going to do, for example, search in IEEE paper, you can type, for example, series resonant converter, parallel resonant converter. You have to go read yourself more about it to learn more and more about it. But it was kind of introduction to the resonant converter, So you guys, what they are. And you know what's the advantage of having them, At least on one side, they do soft switching, right? Either at turn on or turn off. It was at turn on. The one we did it with the inductive load is going to be at turn on. If you go with the capacitive, it's going to be at turn off. But we usually do with the inductive, Now, phase 4. So, I assume you guys all have a very good result for the phase 3. Now, Because if you don't, you cannot do anything in phase 4. If you don't have a good result from phase 3. So in phase 3, what you did, I think you put a P ref here, right? And Q ref, right? And I'm not going to go through the rest. Whatever you did, right? You put the 5 kilowatt, 10 kilowatt, whatever as a command. Q ref, it could be whatever, 0, 10 kilowatt, whatever it is. So, and you go through, right? Now, how we're going to bring the phase 4 in? So basically, phase 4 is going to be like this. Hardware. We have a solar panel, right? This solar panel is connected to the inverter we have. And this inverter is connected to the grid, right? Right? This is what we have. Previously, we had a battery here. What was the advantage of battery? We don't care about this DC plus anymore. It's fixed, right? The battery voltage is going to change, but it's not sudden. It's going to be, for example, full charge 600 volt, come down to, for example, 500 volt. It still is kind of fixed, you know, when you look at it. Now here, I think the panel we gave you, I'm not sure how much it is, 6 amps, something like that. I'm not sure how much it is. 6 amps? It is 6 amps. And I think here, I remember just I checked this for you, about 50 volt here. I think here is about 60 something, 65. We said, how many panels in series? 8. So basically, you can go to the PCM. The good thing for you guys, you have PCM, you know now. It has a, last year they didn't have PCM, because some of them they have to model this one. What you can do, you put an I short circuit, right? V open circuit. If you are going to put one panel, see, 8 panels you can combine it and treat it as one panel. How much you're going to put here? 8 panels.
6 over 8.
Hmm?
6.
6. Why 6?
Here in 2.
You're in 6, exactly. So the current is not going to change. Well, how about here?
8.
Times 8, right? Basically, this one is going to be, it's going to be about 520 volts, right? And this one is going to be 6 amps, right? And here is going to be about 400 volts. See, and make sure here I have about 400 volts, something like that, at the MPPT. PCM tell you, give me this, and give me this and this, which you can find it in the, we can find it in the Excel sheet you have, right? In the Excel sheet, I give you these numbers, right? Create another column, what to do. This one times this one, right? In the Excel sheet, you have one column for voltage, one column for the current, right? Time it by each other, it's going to be power. It's going to give you this one, right? It's going to give, just find out how much is this one. These are, because for the PC model, you need this one. It's going to ask you how much is the VMPPT and IMPPT, right? If you look at the PC model, and you know, the short circuit and open circuit is easy to find out, you know, because you know how much is this time by 8, and this one, whatever it is, you're going to put it there, 6 amps, right? But you can find this one from the Excel sheet you have, right? Now, the solar panel you modeled in the PC, right? Before going even here, forget it. Don't put the solar panel here for the when you are going to do this one. You simulate this case. Put the current source here. A capacitor here, I said how much? 2 millifarad, right? I mentioned 2 millifarad, right? And this is the inverter. And here, right? How much voltage we want to have here? Sorry, let's not go there. Let's say, right now let's go with the 400 volt, you know, the one you had in the phase, previous phase you had, right? So you need to add this one to your loop. You say, okay, I'm going to measure this VDC, right? I want to have a VDC ref of 400. Why I'm going with 400 volt? Because of the 208, right? Of the 208, you know, we have over there. I cannot put 300 volts because 300 volts is not going to give me 208, right? I'm going to have it be in trouble. But 400 volt, 500 volt, whatever you want. 400 volt is okay. Something more than 350 volt, whatever you put is okay. 400 volt is good, and it's going to be very close to this number also. right? This current, you can put it like a variable current. Could be, for example, 5 amps, 10 amps, 12 amps, and I don't know, reduce it. Something you can program this one, or you can go with only 2 stage. This one they exist in the PC. Just I want to say you can change this source here. My point is to change this source. We will not be constant. Now, VDC ref, right? This is the given 400 volt. And VDC, you can sense this voltage, right? In PC, the idea are like this. They show the voltage sources like this, I believe. You put this one here, and here, right? You can set the gain here 1. But in the reality, there is a loop and those things. Let's forget for now. Just you want to know how much is the VDC. You have the reference value, you have the DC actual value, right? PR. The only thing is this PR. If your current loop already works well here, if you have good results here, this piece is just to find this one. And to tell you, maybe you should put a KB negative. Maybe, I don't know, I cannot recall it exactly how much, but maybe you should try KB negative. And usually, if the time constant of this one is about millisecond, go with this one like at 10 times, 10 milliseconds, something like that. And now, connected to whatever you have already, right? And QRF is 0, 1 unit per factor, right? QRF is, in this case, in the phase 4, QRF is 0. So what is going to happen? So you pre-charge this capacitor to 400 volt. When you are simulating this one, put 400 volt here, pre-charge. In reality, we have to do all these things by circuit, just to put the numbers here. But now, when you run this simulation, this is what you need to check. So this is more, you put a voltmeter here. You want to measure the VDC ref, and you want to measure VDC, right? You put another voltmeter here. This is the VDC ref plug. If you get something, so you started from 400 volt, maybe you have something like this, because always there's a little bit transient, right? If you stay on 400 volt, good. This is good. Now, you change your current, right? So what is going to happen? If the current goes up, so the voltage is going to go a little bit up and again come back, right? Any change you have in the current, you see a little bit transient here, and again this one, right? Another thing you need to look at to make sure your simulation is good. Hopefully you did it for phase 1. Phase 3. The one is going to tell you your current control loop are good. Which one is it? ID ref, ID, IQ ref, IQ. So in this case, ID ref is going to be all the time 0, right? It's a unit power factor. So basically, you should have something like this. Boom. But whenever you have a change here, lose the change here again. Whenever you have a change, right? So IQ ref is going to be based on how much current you are putting here, right? So you start from here, for example, this much value. This is the ref value. For example, goes to this much, goes to this much. For example, this is your reference, right? It's not going to be as nice as smooth as this one, but because the output of this PI is going to be Pref, which is IQ ref, right? So now you should see something like this. This is something you need to check. Whenever I simulate this thing, I'll go check, look at my ID, ID ref, IQ, IQ ref. Because if these two are not working, maybe not working. Right? So you do this. You set this PI, you get good results, right? You're 90% down, 80% down, with your phase 4. What's the next step?
MPPT.
MPPT algorithm. This VRF I put here, it should come from the MPPT loop, right? Yeah. It should come from the. You measure this voltage, you get rid of this one, you put the solar panel back here, right? Because think about it, solar panel is like a current source, right? Just I put the current source here, fix my PI first here, right? Now I put my panel here. So this one should come from the NPV, and we explain this one. You measure the VDC and this one. I sold and VDC and this part is the most important, like 70% to fix this one, you know. This one should be easy because there is no PI anything. So like the 2 volt, 1 volt, 3 volts, something like that as a step voltage should be enough. Good luck.